Hello, today we're doing some important things for real analysis. Uh, Hope you enjoy. First, we're covering metric spaces, and they have, so it's a set with a distance function. And the distance is defined as the distance between a point and itself is 0, an element of the set and itself is 0. Otherwise, it's greater than 0. For x not equal to y. Then we have something called the triangle inequality. So the distance between x and y plus the distance between y and z is greater than or equal to the distance between x and z. And the final constraint we have, distance, okay, distance between x and y is equal to the distance between y and x. And so now that we have this, we are going to define something called a neighborhood. And this is pretty useful, pretty interesting. So for a point A in a set, in a neighborhood of A, say an R neighborhood, is the set of all points B such that the distance between A and B is less than R. And so now we'll define what, so now we'll define an open set. So a set is open if for any point in the set, say E open. So if A is an E, then there's a neighborhood of A. This is some notation. There is some neighborhood of A in E for some R. So a neighborhood itself is open because you could just keep going near the border of the neighborhood. Well, let's look at a more concrete example. Say this means this is it's like the same as 0, 1 means 0 is less than x is less than 1. If we had this, it would be less than or equal to so no matter how close you get to one of these, since 0 is not in the set, you could always find, and so no matter how close you get to 0, you could always find, so say it's a point x, the x neighborhood of X would still be contained in this set. So this is open. And then it's set would be closed if there exists a point in the set such that, let's make it new. There exists a point in the set such that any neighborhood you create would contain a point that's not in the set. So you can see how with this less than or equal to, you could just take the point on the end, and no matter how close you get, there would still be a point in the neighborhood that's not in this set. Versus for this, no matter how close you get to the end over here, there's still going to be a neighborhood that's in the set. So that's open and closed sets. Now finally, okay, we need to know what alright, we're making good time. What is alright, we'll get to that later. Now we're going to define a compact set. Well, first, what is an open cover? A set of G alpha. An open cover of E is a set G alpha of open sets, open, such that E is a subset of the union of all G alpha. And so now that we have the definition of an open cover, we define a compact set, compact E, compact set. So every open cover of E has a finite subcover, and this is very confusing. So it might be better to look at this theorem that was proved once I finish writing this out. Of E has finite subcover, a finite subcover. So a subset of the cover that is finite, a union of all the sets in that subset, will be a superset of E. So the Hein-Borel theorem says that on the reals, a set that looks like this, so it's closed. You can see from here, closed, because both ends. And it's bounded. That means that it's compact. So any set that looks like that will be compact. Also note, I described open and closed sets, but a set like this would be neither open nor closed, because over this is like somewhat unrelated, I guess. I hope you're following, but a point right here, there are neighborhoods that contain points not in this set, but no matter how close you get over here, you can still find a neighborhood in this set. So it's not open because of this. But it's not closed because there isn't because there are points that have because yeah, it's not open because of this, and it's not closed. Oh yeah, because there's a point outside the set. They call this a limit point. So that has a neighborhood that contains any neighborhood of this point contains points in this set, and yet it's not in this set. So it can't be closed. So this is neither open nor closed. That doesn't have anything to do with this. Like a little bit of a so the Hein-Borel theorem says a set that looks like this is compact. And so that's sort of, I guess that's probably kind of useful. Now we need to look at connected sets. Connected, but first we need to look at separated. So separated A, B means the closure. Okay, so another, and we're going to have another aside once I finish writing this out, I guess. So the closure means it's the set of all points. Okay, so closure of E is the set of all points. Let's say E is a subset of X. Would be the set of all points in X such that any neighborhood of that point would be contained in E, and that would be unioned with the points of E. So they call that well, that's the closure, I guess. So the closure of this, for a simple example, would be this, because a neighborhood of A would be in the set from A to B. They call this a segment. Any neighborhood of A would be in the segment from A to B. And then they call this an interval. And that's pretty much what a closure is. So a separated, two sets are separated if the closure, so say A and B are separated if the closure of A intersects